In senior one, what was your first topic? Hey, have you forgotten? Daniela, what was the first topic in senior one physics? Okay. Let me not take out of time on that. Let us now look at things that we want to define. Do you know a physical quantity? Do you know what we mean by the term physical quantity in general in science, not necessarily in physics? What is a physical quantity? Who can tell us what a physical quantity means or refers? It might not have a definition specific, but what do you think it refers to?
I think it is like something that can be measured. Yeah.
Very good. Any item that can be measured, something measurable. That I say, I'm going to measure the mass. The mass is what we are going to measure. Therefore, mass is taken as a physical quantity, something measurable, something that you can measure. Can somebody give me any other example apart from mass that we can measure?
Length.
Length.
Time.
Time. Okay. Now with those quantities, in science, we categorize them. Do you notice that some of them have units, others don't have units? Some of the quantities. Can you give me an example of a quantity that does not have units? An example that doesn't have units of a quantity? You have forgotten. I've forgotten many things. You need to read. Any person with a quantity that does not have, let me give you an example. Relative density. What are the units of relative density? What are the units of relative density?
It has no unit.
Hey, so those are quantities that have no units. That's why I'm asking. Give me examples of quantities that have no units. And one of them is relative density. Do you know of any other quantity that we measure, that we find in science, but has no units? Who remembers any other?
Magnification.
Good. Magnification. That's good. There is, do you know refractive index?
Young's modulus.
Young's modulus. Okay, very good. All those ones are quantities that have no units, but they are measurable. We can measure them. We can determine them in science. Now, after knowing this physical quantity, the physics comes in and says, these physical quantities are categorized into two parts. The first category is the one that we refer to as the fundamental quantities. Fundamental quantities. And then the other part, who can tell us the other part? Who can guess? One part is fundamental quantities, then the other one is quantities which are not fundamental. They are what? The senior one works so much.
Derived quantities.
This side we have derived quantities. Have you recalled something like that? Fundamental and derived?
Yes.
Now, after recalling that, the next question is yours. Who can define fundamental quantities? Who can define for us fundamental quantities?
Fundamental quantities are quantities that have both magnitude and direction.
Okay, you have tried, but it's not the actual answer. For you, now what you have defined vectors and scalars. You have gone to vectors. That's why you talk about magnitude and direction. You get what I'm saying? Here we are under fundamental. Okay, do you have any examples of fundamental quantities that you remember? Any example of fundamental quantities?
Mass.
Very good. Mass. We have mass. Any other example?
Temperature.
Temperature.
Time.
Time. Good.
Length.
Length. Good. So we have mass, temperature, time, length. What else do you have? Okay, out of all these ones, we shall have what we call basic quantities. Out of the fundamentals, we have the basic, the major ones. Who can guess the major ones out of these ones that are going to occur in almost all derivations? Out of these ones that you have told me, which ones are the basic quantities, like the most fundamental ones? We have mass.
Mass.
What else?
Length.
Length. And
Maybe time.
And the time. These three are going to occur in all our derivations. Temperature is okay, it's a fundamental quantity, but it is usually used under a specific region of physics. But these ones are going to occur in almost all the things. Now, I want somebody now to define for us what are fundamental quantities. Because when you define fundamental quantities, then the opposite of what we would have defined would be the one for derived quantities. Who can somebody try to remember? You've been in class and remember something.
Fundamental quantities are quantities that cannot be got from other.
These are quantities. These are quantities that cannot be expressed in terms of other quantities cannot be expressed in terms of other quantities. Examples include these ones that we have said. Examples include these ones. Mass, we shall take the three. Mass, time, and length. Those are the fundamental quantities. Those quantities cannot be expressed in terms of any other quantities using any method. And examples are mass, length, and time. So who can now define derived quantities? After defining fundamental, who can define derived?
Derived quantities are quantities that can be expressed in terms of other physical quantities.
In terms of other? In terms of what?
Other physical quantities.
Actually, that is very true, but we don't express them in terms of any other. We express them in terms of the fundamental. They are specific. So these are quantities that quantities that can be expressed in terms of the fundamental, quantities. In terms of the fundamental quantities of mass, length, and time. You be careful with that definition that I've written. These are quantities that can be expressed in terms of the fundamental quantities of mass, length, and time. We are very specific on this definition. If somebody just says these are quantities that can be expressed in terms of other fundamental quantities, full stop, we don't mark. You must tell us what fundamental quantities are you referring to. These are the ones of mass, length, and time. Am I clear? Am I clear, people?
Yes.
So now I want you to,
Yes.
I want everybody to give me one example of a derived quantity. These are very many. Each person give me one or two examples. I start with Anthony.
Then
Shall we have volume?
Volume. Then Daniela.
Area.
Immaculate.
density.
Next person, Kristen. Application. Waji? Sorry, someone was calling. Christine, I didn't hear your answer. Christine, I didn't hear your answer. Is Christine on? Rebecca Angel, her microphone is off. Okay, with those examples, let me now. There's this statement I want you to see. Physical quantities that are not related to mass, physical quantities that are not related to mass, length, and time are called dimensionless. Listen to that statement. We have said, we have these ones. We have fundamental quantities, we have derived quantities. And we have said that derived quantities are those quantities that are related to mass, length, and time. But we have other quantities that are not related to these ones. Those quantities are said to be dimensionless. Dimensionless. So dimensionless quantities are those quantities that are not related to mass, length, and time. Yeah, teaching physics. Just to show. I was saying physical quantities that are not related to mass, length, and time are called dimensionless quantities. Some books call them non-dimensional. Now, these quantities, this is where we mention things like relative density. We mention things like mechanical advantage of a machine. Mechanical advantage, we have refractive index, we have logarithms, trig functions, something like that. So those are called dimensionless quantities. I was asking my teacher here to show me these books. This is a book. These are some of the textbooks that you can buy. This is a book in the names of Advanced Physics by Tom Duncan. Advanced Physics by Tom Duncan. You can buy some books like this. These are all textbooks in A-level. For those, have you started buying some books? Have people bought some books here in this class of physics?
Yes.
Which ones have you bought? Let us now define dimensions of a physical quantity. Instead, I will send you some notes so that you can follow from the notes. Dimensions of a physical quantity show the way a physical quantity this is derived. This is a definition that you need to understand because we're going to use it. The way a physical quantity is related to the fundamental quantities of mass, length, show the way a derived quantity is related to mass, length, and time. Don't forget, we have said that the fundamental quantities are three: mass, length, and time, that we shall discuss. But all other derived quantities that have dimensions, that have units, are all related to these three. Some of them use two out of the three, others use all the three in their relation. But all the physical quantities that have dimensions, that have units, are related to these three. And how are they related? We shall always cross-check their relationship by following what we call dimensions of a physical quantity. Let me hope I'm clear of this statement. We are now starting to do the real work. Dimensions of a physical quantity show us the way different quantities are related to the theory. And we are going to get examples. First of all, the symbol for dimensions. This is the symbol for dimensions. We use something like this. We use square brackets. Symbol for dimensions. This is the symbol for dimensions. So every time you see those brackets in this particular topic, those brackets will be referring to the symbol of dimensions. Now we want to get examples because we have said all the other derived quantities that have units are related. All the other derived quantities that have units are related to the three fundamental. But how are they related is now our question. First of all, the three fundamentals, we have said we have mass and dimensions of mass. We shall write them like this. M. That's how we shall be writing the dimensions of mass. Once for time, we shall be writing letter T. And then the one for length, shall always be writing N. That's how we shall be representing dimensions of a quantity such as mass, a quantity such as time, and a quantity such as length. That's the symbol of dimensions. Now, let me start with this example. Do you know area? Area. What is the formula for area? Who remembers area? What is area? Now we want to see how are those other derived quantities related to the fundamental. That's our target right now. Somebody tell me, what is area?
Length times width.
Area is length times width. Now, when you look at length times width, we want to write these letters. We want to write these quantities in terms of these three. So where there is length, it will be, because length is part of our theory, this will remain as length. And its units are meters, this one. But where there is width, here I have mass, time, length. I don't have width. So how will I write width as regards to these three? What can I write here where there is width?
L.
Also, width is going to be the same as length, because width also has units of length. So I will write this as length times length. You can even see from the units, meters squared. Meters squared is the same as L times L. So this one is the same as L squared. Am I clear to people here? We are going to rewrite all those derived in terms of these three. Some of the quantities will take up all the three. Some quantities will take up only two of the three. Others will take up one. Like area. Area has taken up only length. Area is expressed in length alone, but his length is squared. His length squared. Now, how do I write the dimensions of area? So I'll say dimensions of area. Dimensions of area are L squared. Dimensions of area are equal to L squared. Is there any question? This girl again has gone off. Is there any question? Hey, Nagai, you're welcome. Nagai, we have talked about dimensions of a physical quantity. Dimensions are like units. In science, all quantities that have units, like meters squared, kilograms, all those quantities have dimensions. And the dimensions of a quantity is just a way how that quantity is represented. In terms of these three, before you came in, we talked about fundamental quantities and derived. Fundamental quantities are the ones that cannot be expressed in terms of others. Fundamental, you can never express them in terms of others. And in science, we have three major basic fundamental. Those include mass, time, and length. But if they are not fundamental, then they are derived. Therefore, we said for derived quantities, those are the quantities that can be expressed in terms of these three. So we have derived and fundamental. Fundamental, you cannot express them in terms of others. But derived can be expressed in terms of mass, length, mass, time, and length. That's what we started with. Now we came up to this statement of dimensions. Now, those that are derived, such as area, they're asking us, so how are they related to these three? What is their connection? How is area connected to these three? So that we are writing here, we start by getting the formula. Area is length times width. Length is already here. By the way, these square brackets are the symbols of dimensions. When they ask for dimensions of a quantity, you don't have to write the whole word dimensions. Just put the symbol square brackets. Then you put what you're looking for in the inside the brackets. So here we are looking at dimensions of area. Dimensions of area. So area is length times width. Where there is length, I put L. Also, where there is width, I put L because L is what we want. We want length. We don't want to use any other quantity apart from these three. So you have to get ways of changing that letter, that quantity in terms of the three. So L times W, which is L times L, which is L squared. So the dimensions of area, are L squared. Mr. Abraham is on and off his internet. Am I clear, people? Especially that guy who has just joined. If I'm clear, can you get for me the dimensions of volume? Volume. Get for me the dimensions of volume. People, get for me the dimensions of volume. Who has got the answer for dimensions of volume?
The answer is
Are you working out? Rebecca, are you working out what we are saying? Hey. Daniela, are you working out?
yes. The answer for the dimensions for volume is L cubed.
L cubed, good. Abraham, your internet, I think, is disorganizing you so much. But are you now on? Are you able to see what we are writing? Abraham, can you unmute and talk to us?
Yes, yes. Bro, you're fucking.
Okay, volume. We have just talked about things like this. These brackets are symbols of what we call dimensions. Chapter, I think we're also following. So we are going to write volume in terms of mass, time, and length. But we know volume is length times width times height. So if I'm to write these three letters using these, I'll say where there is length, I put length. Where there is width, I still put length. Because width is the same as length. Meters, same unit. Eh? Where there is height, I also put length. So I'll write L cubed. As the dimensions of volume, by the way, you have to note, some people make this mistake. They do like this. They say dimensions of volume. They do like this. What do you think is the problem with this writing? With this one here? What would be the problem? Why do you think this is not right way of representing this? Kristen, why do you think this is not right?
I think it's not right because that would be making the dimensions of volume the dimensions of L cubed.
Okay, yeah. This is like you are saying, dimensions of volume is equal to the dimensions of L cubed. Repeating the same statement, dimension. Yet, it's dimensions of volume that are equal to L cubed. So be careful with the way you're writing this. Okay, who has got for me the dimensions of speed? The next part here was speed. Who has got the dimensions of speed? You just have to get the dimensions. You first have to remember the formula, the general formula of speed. What is speed? Who remembers what speed is? Anthony, what is
Product of distance and
What I know
time.
is distance traveled over time elapsed.
distance divided by time. So for this case, we shall get the dimensions of distance divided by the dimensions of time. What are the dimensions of distance? Remember, all the quantities you are talking about here must be in terms of busy theory, mass, time, and length. That's what you have been saying. So what are the dimensions of distance?
L.
Length.
It is length, letter L. The other thing I didn't talk about, these letters are capital letters. By the way, you must have told me there's something which is not right here. Here, I should have written like this. This one shouldn't be on this side. Didn't see that. This one should be dimensions of mass are equal to that. Dimensions of time, and then the dimensions of length. This is the right way, and not the other way around. Okay. L is the distance, is the dimension for distance. The dimension of time is t. Do you agree that this expression can be written like this? You can write it as L T -1. Do you agree with that?
Yeah.
That we can write this one as LT -1.
Yes.
This is how we shall always present our answers. When they ask you to get the dimensions of a quantity, you do like this. Now, somebody get for me the dimensions of acceleration. Acceleration. And then somebody gets for me the dimensions of force. Let us work out together, people, these ones. And then the dimensions of pressure. Let us try out these ones.
Dimension of acceleration is LT to power negative.
Okay. Class one, that one is a message. That's far as what answers do you have? Somebody was talking about the one of acceleration. Acceleration, what answer do you have?
LT to power negative 2.
Negative 4. Eh? Abraham, you have the same answer.
Yes.
Which one do you have? LT?
To the power negative 2.
Yeah, yours is negative 2. The one for Zid Daniela, it was negative 4. Anthony, which one do you have?
And you have LT power negative 2.
Negative 2. That guy, which one do you have for acceleration? That guy is on. Rebecca, which one do you have for acceleration? Kristen,
I have LT to the power negative 2.
okay. I think most people have that. You can work it out together here and see. That guy, you have not replied. I don't know that you are doing the work. So acceleration first of all, what is acceleration? Acceleration is velocity out of time. Velocity out of time. But velocity is the same as speed. Velocity is equal to displacement out of time. That is velocity. Displacement is L T, which is the same as L T negative 1. So this is velocity. This implies that, therefore, acceleration will be L T negative 1 divided by T. Divided by T, which is the same as L. Now you look at the powers of T. This is T power negative 1, and this is 1. Mathematically, it's the same as T to power negative 2. How do you get negative 2? You get negative 1 down minus the 1 down. I mean, negative 1 up minus the 1 down. And your answer here is negative 2. So that's how this one is achieved. Let me hope we are together. People who didn't speak to me, are we together?
Yes.
Okay, now, who has done force? What is the answer for force?
MLT power negative 2.
MLT power negative 2. You all have the same answer?
Yes.
Immaculate, do you have the same answer?
Yes.
Okay, MLT to the power negative 2. What about pressure? You also add on power. What about pressure? What answer do you have for pressure?
That's a need
Did what?
explanation.
Pressure. Okay, maybe somebody has got it. Rebecca, what do you have for pressure? Actually, what do you have for pressure? You have L what?
I think it is MLT negative 2 out of L squared.
Okay, you simplify it. You simplify it to the last one.
Teacher, to continue from where she has stopped,
Hey,
I think it is ML negative 1 T squared.
ML, let me see. When you continue, you have ML negative
1
then
T squared.
squared. Okay, somebody has this. Who else has a different answer for pressure? Okay, we can work it out together and see. Let us see. We can work it out. We said always first remember the formula for that. Somebody should mute. Rebecca, you mute. Mute yourself. What's the formula for pressure? Pressure is equal to force out of area, isn't it? You have just told me that you got the dimensions for force. What are the dimensions for force?
MLT to power.
You said ML and what?
T to power -2.
T to power -2. And then area is L squared. So when you work on the powers, let me hope you all agree that force is ML T to power -2. When you work on the powers indices, which I was showing you indices yesterday in math. Indices, we shall look at M. M will remain the way it is, but L has a 1 up and a 2 down. For indices, remember, if you have 1 and the 2 is down, it's like you are subtracting. You subtract 1 minus 2, and you end up with -1. Then the T, we only have T, so this one I leave it the way it is. So that's how it. By the way, T, Anthony, your T was not right. You didn't put a negative on your T. Up, don't you told me?
Yes.
You have now seen it.
Yes.
Now, Nagai, are we together?
Teacher, what if you use this formula, pressure equals to density times height times acceleration due to gravity?
Even if you use those ones, the answer will come to this. Only that you will pass via a longer route, but you still, because the dimensions are the same, irrespective of the formula you use. Now, different formulas will take you maybe longer, but you come to the same answer. Because if you have used that formula, it means because the formula has pressure is equal to density H this. You see how many quantities? One, you get the quantities of density. You have to get the quantities of density. By the way, you're also going to get the quantities of density. Then the ones of height are known. Height is the same as what? Height.
Length.
Height is the same as length. Then acceleration due to gravity is the same as acceleration, which you have already got in part, I think it was our number 3 or number 2. Acceleration due to gravity is the same as acceleration because it has the same units, meters per second squared. What are the units for acceleration?
LT to power -2.
Acceleration. We said LT meter this one. So you are going to combine this, combine it with this in the multiplication, combine it with density. Somebody tell us what are the dimensions of density? Who can work out the dimensions of density? Work them out very fast and you see the answer. By the way, one simpler way of knowing those things, if you don't want to over-derive, you can go to the units. You can start from the units. For example, density. What are the SI units of density? Kilograms per meter cubed. You remember this, eh? The units of density, kilograms per meter cubed. Now, kilograms come from what? Kilograms come from mass. So I'll put here mass, M. Meters cubed is length. So I'll length, and I put a -3. So you can get the dimensions just from the units. Just follow the units. What are the units? Like in acceleration due to gravity is meters per second squared. Meters is L, length. S squared per second is squared is time. So this can be got from this. Now, what I want you to do, I think it was Rebecca who was asking, we are going to combine these three quantities in this formula, and we see whether we shall come to the same formula like this. Whether we shall come to this. Because dimensions do not change irrespective of the formula that you pass through. Take it there. So I want people to help me multiply all these quantities, these dimensions, and see whether we shall come to the same as this one. So that is what the workout I'm expecting people to do now. We get the same density when you look at that, we get the same answer.
Teacher, ML -3.
You get the same answer.
I can see ml to power negative, to power 5, t to power -2.
There was ML. Sorry, this one had a negative. You notice here, I've got a negative. This is -3. So there was a -3. You have seen that. There was a mistake. Multiply again with the -3. What do you see now? People are not sober. You didn't even notice that I'd forgotten a -3. Hey, wait, we don't play sober in class. Be in class. So when you multiply, you come now to the answer that you were expecting.
Yes.
Yeah.
Okay, so our conclusion here is, irrespective of the method, the formula you use, the dimensions of a quantity do not change. That is what we are trying to conclude with. The dimensions of a quantity do not change. Who has got one for power? Power.
Me.
What is your answer for power?
ml to power 2 t to power negative 3.
M L power 2 T power negative. This is what you have got. Eh?
Yes.
Should I assume it is the correct one for everybody? Do you all have the same? Some people have kept quiet since the lesson started. Please, you reply. You have to be active in class. That is how A-level is going to be managed. A-level needs a lot of participation, especially from you, the learners. Rebecca, do you have that answer for power?
Teacher, how do you get it?
But when you know the same answer, then you don't keep quiet. Because now I was going to go to the next part. I thought people had, since people are keeping quiet, they had all got the same answer. Don't keep quiet. You have to say, teacher, I've not got that answer. Don't wait for the teacher to ask you that, Rebecca, have you got the answer? It's you. When you see we are putting something on the board and you have not understood, you tell us. You put up, you cannot hand on that platform. And since you are still very few, you can say, teacher, I've not seen, I'm not getting the same. Then you tell us what you are getting. People, be participative in A-level. Don't keep quiet. This level becomes very important if you participate. And now we are going slowly because we want you to pick up the concepts. This is going to be the first topic teachers will teach in class, but they will be a little bit fast. So you better use this opportunity that you ask the teacher before we go to the next step. Nagai, do you have the same answer? Nagai, unmute and tell us. Kristen, do you have the same answer?
Yes, I do.
Okay, we can go together as we hope others who have not understood it. I see 1, 2, 3, 4, 5, 6, 7 participants, but on the list, I think all of you have not yet paid for physics. For those who have not paid, please remind your parents to subscribe. Eh? As you pay, you also remind your other colleagues. I know you have so many friends who are not yet enrolled. Tell them classes have started and we are actually doing the real work that we shall be doing at A-level. The time might not be so sufficient when you return to school. They might put you under a very tight schedule and teachers will be just sending notes to class, people copy, we have finished this topic. So you tell them that they don't miss out this opportunity that we interact with you people. Let us work out power together. For those who have got the answer, what did you start with? Power is equal to what? Power is the rate of doing work. Eh?
Yeah.
So power, I think, is what done?
Over time.
Over time.
Yes, out of time. But what is work done? Work done is force times distance. Force times distance. Out of time. I continue putting these brackets until when I put the letters. When I start writing those capital letters of M, L, and T, that's when I stop putting the brackets, but I continue putting these brackets because I'm still looking for dimensions. The dimensions of force. Somebody talk, what was the answer for force? Dimensions of force.
MLT power negative 2.
MLT power negative 2. The ones for distance is L. And the one for time is T. Now indices. Collect the terms that have similar bases. M is alone, so we leave it there. M has no other term, so M will be there. After M, I go to L. L has, this is L to power 1. This is also L to power 1. So 1 plus 1, because we add, since we are multiplying, 2. I go to T. This side In the numerator, t is -2. It's like this. T is -2. The denominator, t is 1. We subtract. This gives us -3. So that's how we get that answer. Rebecca, Chitegede?
Yes, teacher.
Okay, people. That I don't want to add too much on that lesson. That is our first lesson for mechanics today, and I will not add on any other part. For those who didn't join in the first part, we have said in this lesson, we categorized physical quantities as fundamental and derived. And we defined fundamental quantities as the quantities that cannot be expressed in terms of other quantities, fundamental cannot be, they are independent, they are standalone. And examples, the basic ones include mass, length, and time. And I said there are others like moles, electricity, temperature. Now those ones can be fundamental, but we don't normally use them in our derivations. That's why we picked the 3 to be the most fundamental: mass, length, and time. Then we said derived quantities. Those are the ones that can be expressed in terms of these 3. Don't just say can be expressed in terms of others. You categorize, you tell us which others are you referring to. So these ones, derived quantities, are the quantities that can be expressed in terms of the fundamental quantities of mass, length, and time. After that, we gave examples, of course, the power, pressure, volume, what. Then after we said dimensions, other quantities have no dimensions, have no units. Those ones that have no units are given a name. In physics, quantities that do not have units are said to be dimensionless quantities. Dimensionless. Some people can call them non-dimensional quantities. Those are the quantities that have no units. We gave examples of relative density. We have refractive index. We have mechanical advantage. All those quantities have no units. Therefore, in physics, we refer to them as dimensionless quantities. Then from that, we said, okay, after knowing what dimensionless are, and those are with dimensions, what is that exact definition for dimensions of a physical quantity? Then we said dimensions of a physical quantity is just a way how derived quantities are expressed in terms of the fundamental we have talked about. So dimensions of a physical quantity is a way, or shows the way a derived quantity is related to a fundamental quantity. This is what we are trying to show here, how power is related to this fundamental, how pressure is related to the fundamental. So when they ask you to define dimensions of a physical quantity, you just say, this is the way, it shows the way how a derived quantity is related to fundamental quantities. And after that, we gave examples of how we can relate all those derived in terms of the 3. Those are the ones we have talked about today. These are examinable questions in mechanics. So far, we can now form a full number of 20 marks from what we have just discussed today. I'll put this video, I'm trying to record it and see if I can put it up on our cloud for you to watch later. For those who are on and off. Thank you so much for being in class, a good class. Just request you to inform others who have not yet joined that real work is taking on. You should come on board from any school. You should come on board and we start this work. Thank you so much. Have a nice time. Unless there is a question. Is there any question from one of you? Is there any question? Is Abraham still present? Is Anthony present?
Yes, sir.
Is Daniela present?
Yes, I am.
Is Kristen present?
Yes, I am.
Rebecca?
Yes.
Shaima? Nagai Shaima, are you present? I think her network, because I see her on. Immaculate can't hear us because her microphone is not on. She has not joined with computer audio. Hey, she's back. Immaculate, are you on now? Immaculate.
Can hear you.
Okay. Shaima is on who has not answered. Shaima and Abraham. I think they are off.
I'm here.
Oh,
I'm here.
Shaima, can you say something to us? Are you on? Unmute and say if you're on. Okay, people. I just ask you to go and get any other quantities that you have ever learned and get their dimensions. We have been doing these ones. There are so many. We have done like 2% of the quantity. There are very many that we have not discussed. But if you can't get some time, go and pick all those ones that you know, get their quantities, in that you get used to the work that we are doing. Okay, thank you so much. Have a lovely day.
Thank you for teaching.
Welcome.